So we're going to probably put parts 2 and 3 together. That was all theory, but this is practice. How is SPR actually used to measure protein binding in a BIAcore instrument, and what are you going to be doing in May once we set these things up? So remember that we talked about this whole phenomenon, and the whole last lecture was explaining why when you shine a light on an interface, do you get a shadow based on the refractive index at the other side. But the main thing is, you can get here they show an antibody bound to the interface. So the antibody has 2 arms, and you flow the antigen over. The antigen binds to the antibody, increases the mass, changes the angle, which you don't see, but it moves the changed angle is turned into a resonance signal for you. It's just response units. So it's like unitless, meaningless unless you calibrate it properly, that kind of thing. Resonance signal is related to mass. And by the way, 3410 students, you won't get to this until we actually have our lab due in lab 4 at the end of the quarter. There is an equation that relates response level to mass that is attached to the chip. And I will let you use that equation. You have that to look forward to. That's a long time in the future. But realize that this happens in real time. You don't have to label either protein. You just have to attach one of the proteins to a chip. So it's minimally invasive in chemical terms. And the change in resonance signal is directly proportional to the amount of protein bound. That means you can figure out what's going to be bound. The one thing is you have this machinery that's going to flow water through the channel that is right below the chip. You have a gold chip, and now I'll be able to, actually I have a picture of one. You'll be able to see it when we go in the lab. And then you have the IFC is the flow apparatus that flows water over the chip. You don't really have to worry about it. You just control it sometimes, like you open and close valves on it. The way the IFC works is it actually, so you have the chip that's a flat surface, and the prism is actually on the bottom. So that's why this is sometimes flipped over. This might look flipped over, but this is the way it physically is. Actually, it might be flipped over in ours. Yeah, this is actually upside down from the way it is in ours. So it's always upside down. Always look for the prism. You know the light's on the side of the prism. And on the other side, you have the water, and it has channels in the IFC. And when you look at it in the lab, you'll see it's orange. It's orange because it's orange rubber that can be depressed by air. The way that you open and close valves within this, you see there's open valve and closed valve, and you have different flow cells within the IFC, and you can flow stuff through by opening and closing the valve and then just pushing it through with a syringe pump. So the one thing you should be ready for when we do BIAcore is it's going to be loud. Well, not really that loud, but it's going to be sudden hisses of air. It's going to be a little bit like a steampunk factory or something like that, where you have these sudden, it's actually pneumatic in a certain way, because you're using the air to push on the rubber part of the IFC and to open and close these channels. You'll get used to it really fast. It's just that it might startle you a few times. That's normal. The other thing is, how many flow cells do you have? Most big BIAcores have 4 flow cells. That's all I could find a picture of. Ours is actually an earlier prototype, so it only has 2 flow cells. But the important thing is that the stuff flows through flow cell 1, and then it flows through flow cell 2. There's a split second where the sample flowing through hits flow cell 1 first. And this is actually going to be important when you look at your data. You want to remember flow cell 1 gets the sample first. So this is what the flow cell actually looks like. You don't really have to worry that much about it. Here's an example of the flow. It's going through, and the valve where it pushes the air through. This is just so you know what to expect. You expect something pneumatic. There's going to be an air compressor, and we are going to be using compressed air. But you don't actually touch any of this. The computer controls all of this. And it moves stuff through the different flow cells. It's very small. So you're going to be using like just a minimal amount of reagents. That's it's a really nice technique for that. Okay. So if you have the chips, the different kinds of chips, you notice that all of these have gold in them. You've got to have the gold on the chip. And you have CM5 down to C1, and then you have different kinds of chips. And then you can buy just a plain gold chip if you want to really do whatever chemistry you want on that. The one we're using is CM5, which stands for carboxymethylated dextran. It's a dextran layer, which again is like seaweed. This is our second seaweed metaphor of the day. Dextran is just, it's a version of polymerized glucose. And all it is sugars. It's basically sugar hair on the surface of that chip in a very thin layer. And the different numbers are different ways in which the sugar has been modified. It's been oxidized. So when you take a carbon and you oxidize it, what kind of charge do you set up on that? You're taking a carbon and you're turning like a CH3 into a COO. What charge develops on the COO? Exactly. So you know that this is going to be negatively charged. You're going to have, and it's also going to have a lot of active COOs. So we want to use that to latch on to the sugar hair. We actually also use this chip, but that we've actually used both of these chips. And yeah, but this year we won't. We're using all CM5 chips this time. So I'm not even going to talk about those. Here's a little thing that tells you how thick the dextran layer is. It tells you how carboxylated it is. CM5 is highly carboxylated. Maybe you want a little less carboxylation, you buy CM4. And the other thing is, down here at the bottom, you have an NTA, which actually is related to the column that we use in Biochem 2 to purify. So Julia Rosemary Afra, your poster is going to include nickel NTA. In fact, I think it's in the title, isn't it? You can actually get a BIAcore chip that has NTA on it. And we got it. It actually works okay. You can get one for lipids. Basically, if you can figure out how to chemically attach it through a covalent bond to a chip, you can either buy or make a chip for it, for BIAcore. Here's the organic chemistry for those of you into organic. What we do is they use an N-succimidyl group. And it's called amine coupling because you have the carboxyl on the dextran. You add the N-succimidyl group, and that activates it. Then when you flow a protein over, any amines on that protein, any positively charged nitrogens, can then displace the succimidyl. When they do that, this bond is broken, this bond is formed, and you have an amide, a nice tight covalent amide bond. The one thing about this, once you do this, you're not going to reverse it. You're not getting that carboxyl back. So this is an irreversible coupling step, and we keep using the chip as long as we can after we permanently fix the protein to it. There are other ways. I haven't never actually used any of these other ways. You can add through thiols on the protein. You can add through aldehydes on the protein, although then you have to create an aldehyde on the protein, which is a pain. Or you can do it through malamides, which is if you modify a thiol to make a malamide. Anyways, these are all pains, okay? The amine coupling is the thing. A lot of proteins have a lot of amines on them. And the one thing to realize, when we couple them to the chip, they are basically going down sort of randomly, and there's a certain proportion that might bind face down. That's just what we deal with. So you realize that this is a random amine coupling, how it selects the amines. So we use this, and actually this amine coupling chemistry shows up in a lot of places. Now that I know where it is, you actually see it all over the places. This is a group that actually developed a way to make fingerprints glow. You know, you always dust the fingerprints and you see them use the tape to pull them up. Well, what if we could dust them with glowing dust? And their idea was to use nanoparticles made of zinc, and then instead of like pulling them up with paint, you you basically you do this with them. See how this has succimidyl groups there. This is actually EDC-NHS. These are the exact chemicals that we use to make our chips. Okay, so we use this to attach the protein to our chip. They use it to attach the zinc particles to the proteins in the fingerprint, and that means that you get a nanoparticle coated fingerprint. The nanoparticles glow under certain wavelengths of light. So you end up with a green glowing fingerprint, which at the very least it'll look cool in the movies if it ever catches on. The other thing is when you need to make a quick bond to a carboxyl, this is the way that actually nature does it. There's actually this is a way of doing it. This is making covalent bonds for, this is inspired by the way barnacles make covalent bonds. But again, if you're looking for an easy way to make covalent bonds to amines, what you do is you use N-succimidyl groups. If you want to go into a little more detail about this for a lab report, if you want to have an organic chemistry focused lab report, I'm always keen for students to follow their interests. So you can talk to me if you have an interest like that, if you're in 3410. So the other thing is that, so the general way that, and I'm going to probably do this for you, and Chinyang, you'll probably be testing some of these for me. What you do, but this is going to be in your lab report. What you do is you have your flow cell, you're measuring your flow cell, and you're measuring the zero response. When you put EDC NHS in, that means that the response goes up very slightly because you're putting your N-succimidyl groups on. By the way, it goes up a lot when you're flowing it over because it has a different refractive index. What matters is where do you return to. So this level goes up because you've added your N-succimidyl group. Then you flow your protein solution on. And what you need to see is you need to see an upward slope with an increased baseline after you flow buffer over again. This distance is the amount of protein that has been put onto your chip. Then you might still have some N-succimidyl groups that haven't been kicked off yet. So what you do is you add ethanolamine. That's step 3. Step 3 will kick off all the remaining groups. You see how it's an amine, and so it will work through. It'll provide amines to react with the remaining stuff, and then you should have a nice chip, covalently bound protein, and hopefully it works well for you because there's no going back. That chip is basically committed at that point. This is something that you might want to go after. And again, the weird thing about this is it takes us a month to do these experiments. And so you'll be writing about this, but one of the reasons I'm recording this is because I want you to have this to go back to at the end of class in a month. You'll be writing this lab report. So this is the drawback of BIAcore. You have to immobilize something. It has to be next to the chip to see the plasmon resonance. And so what you do is you have to make sure, and remember, the chip is negatively charged. The dextran has a lot of carboxyls on it, and so you're flowing a positively charged thing over, and you need to make sure that your protein is positively charged. If you remember your biochemistry, the proteins needs to be at a pH that is below the pi. If the pH is below the protein's pi, it will be positively charged, and it will associate with the surface. So you don't know exactly which pH will be like this. You can have a guess, but you have to check to be sure. And so there's a step that you do before you do the amine coupling chemistry called pre-concentration. What it means is you're checking to see if your protein will pre-concentrate, will attach onto the chip. I'm not 100% sure. Some years I ask students to do this, other years I do it for them. We will have to see when we get to it. But this is what pre-concentration looks like. Basically, you're looking within the injection because that's when the pH is changed. And basically when you have pH, you test acidic pHs, and you want to have a pH that's acidic but not too acidic because you don't want your protein to be damaged. And you see here they're trying pH 5.5 and they see it go up a little bit, but 5.0 and 4.5, they both get you a big response. And so pH 4.5 is immobilizing the most ligand, and it looks like we should run our reaction at pH 4.5. So when you talk about pre-concentration, this is all it is. You just try different pHs, and then you put the protein, you see how much protein binds. The higher the line, the more mass is bound to the chip. So this is what the fancy BIAcore looks like. BIAcore T100. This is like the, I think this is the latest model still, because they haven't come out with a new one. And you see it looks all nice and fancy. You basically have the chip that goes in here, you have waste bottles, you have a computer to measure it, and you have a needle which will move through and it will pick up your samples for you, and you can basically program it and then run it all night. What we have is not this. We don't have this. There's the BIAcore 3000. This also has a needle. It's a little bit older. This is the one I learned to use back 20 years ago now. The chip goes in here. It has a little needle that will pick up your samples, put them through. It has a waste bottle, inlet, outlet, and a computer. Again, we don't have this. But what we have is we basically have this without the needle. We have a BIAcore X, which is not a BIAcore 3000. Here it is. You don't see any needle on it. The chip goes in here. But the optics, this part of it, the laser, the prism and stuff like that, are not quite as good, but almost as good as the optics in the more recent ones. So they've upgraded the optics slightly, but the main thing that they did is they added a auto-sampler needle. Well, guess what? You all need to learn things like how to deliver samples repeatedly to a chip. So you get to be the auto-sampler. You get to do it hands-on and learn how BIAcore works. This is how we're able to do BIAcore technology at an undergraduate institution. So the prism, the chip, and the IFC are located here. One thing that might happen is that sometimes the chip gets stuck, in which case I actually have to open up the BIAcore and I have to unstick it. Only I should do that, and so I'm not going to ask you to do that. I'm not going to let you do that. That's the one time when we might actually be able to open it up and take a look inside it. So you have buffer at an inlet, and actually the pump is just a syringe. It's very simple, but it's effective and it works. And the outlet is over here. The injection port is also right there. So you remember how all of you except Deanna, and Deb, of course, because you're in a different class, you've all injected samples onto the FPLC already. Actually, it's different but similar. You're going to be actually pipetting a sample into a small tube, and it's actually a good thing to learn, to be able to have that sort of feel for how it is to use an instrument like this. So the main thing is you always have to keep an eye on your inlet, that your inlet has buffer in it. It flows through here. You inject with this sort of beige spot right here, and it flows out there. And yeah, that's what you have to keep an eye on. By the way, it moves so slowly. It moves at like 50 microliters per minute. So that means that you're not going to be worrying about it running out while you're not looking. Here's the basic steps, and basically we're going to do all the way through immobilizing the ligand onto the sensor chip. We're probably going to do that for you. Your job is going to be injecting analyte and recording response. So you'll be injecting, seeing what the response is, and then the other thing that you might have to do is regenerate the surface. Sometimes what you have sticks so tightly that then it just stays on there. Well, you want to use the surface again, right? And then we're not talking about the amine coupled partner. We're talking about like the antibody that you're flowing over it. Sometimes the antibody just sticks. So realize that this pre-concentration is what we just talked about. The immobilization is what we also just talked about. But mostly what you're going to be doing is you're going to be injecting the analyte and regenerating the surface. And then after all that, you'll collect your data, and you'll have a week or so to analyze it, and we'll have a class about analyzing and fitting the data at that point. But this is the theory. We're going to talk about analyzing the data after we have data. So what's the data going to look like? And that's the last topic in part 2, and then I'm going to talk specifically about what we're going to do. So the power of BIAcore is that it tells you the amount of mass in real time that's associated with your surface. That means that you don't just see how high the mass is, but you see how fast it's curving up to its maximum. And then you stop injecting it and you watch it fall off. and so you watch it dissociate. So that's the cool thing about BIAcore. Technically, we don't talk about kinetics in PChem until we get to chapter 6 and 7. But technically, BIAcore deals with chapter 4, which is equilibrium measurements, and also chapter 6 and 7, which is kinetic measurements, how fast. In a couple days, we'll be talking about equilibrium, which is how much binds. So this is there's a lot of examples of what SPR data looks like, but basically you have a time when you're injecting it over the surface, and you inject, like here's injected 6 different concentrations of protein over the surface. You inject more protein, the blue lines are more protein injected, and the more protein you inject, the higher your response is. This is kind of a cool example, because what they have is they have the ACE2 receptor attached to the chip, probably amine coupled, and then they flow over it the receptor binding domain. I think you can see right here, if that doesn't ring a bell yet, you can see SARS-CoV-2. This is the SARS-CoV-2 variants. And if you look at these, you can see the different variants that came up. And this is actually a while ago, and now these variants are in the past. But at the time, they were just coming on, and people were wondering, okay, why are these variants more virulent? Is it because of receptor binding, or is it because of something else? So they measure the receptor binding, and realize that each variant has multiple mutations. But what they do is you can even see it from the back of the room. You can see that wild type, you see binding. And by the way, these are all the same concentrations. And you see it bind, and then you see it fall off. When you have this N501Y mutation, you see about the same going on. This part is, the left part is the same. But the right part is falling off slower. This means tighter binding. It's sticking more when it has this mutation. This one, on the other hand, the K417N by itself, doesn't bind more, it binds less. And you can just see that by comparing the heights of the peaks. But also notice K417N does not show up by itself. It only shows up in combination with the other ones. When you put it in combination with the other ones, lo and behold, you get your binding back. So basically, the mutations that occurred in the virulent variants were also the mutations that caused the receptor to bind tighter. And you can even talk about the kinetics of it, because this line is flatter, it's falling off less. And that's all there is to BIAcore. You're really looking at a snapshot of exactly what's going on. And from these, you can calculate what the affinity is. And this is everything that we're doing. They calculate equilibrium constants. They calculate on rates and off rates. So chapter 4, chapter 6 and 7, and we will talk about those as we go through. The thing to realize is that thermodynamics and kinetics are very different ways, and so you get good information from all of it. A big K constant is equal to 2 little k constants divided, but that means if your K on is high and your K off is low, you'll get the same big K as if your K off is low and your K on is high. Or actually, because they're divided, I think the low-high distinction might be a little bit confusing. But the main thing is the ratio doesn't tell you whether it's fast on, slow off, or slow on, fast off. Or, I'm sorry, because it's dividing, I keep saying it wrong. It can be fast on, fast off will look the same as slow on, slow off. I need to have the slows together for it to become compensatory because of the dividing. Anyways, we'll talk about all this when we get to it. And I want you to see that in May, this will be our topic for discussion. But you do actually get useful information from the kinetics. And this equation is what's really important for you to understand eventually. The other thing is that you see that they go up to a maximum. The maximum has value for saying what's the most we can bind to the surface. And the maximum for these two is pretty close to the same. Although reaching that maximum can be slower in the slow on case. It takes you longer to reach the maximum. So we'll be working on this as we go through. There's one graph which is kind of cool. This is We'll probably return to this when we get to it, but because KD, the big KD equals little kd over Ka, then you can actually have a graph where you have these two things on the axis, and the KD will be diagonal lines. And you can actually represent kinetics and thermodynamics the same way. This really works out so that the northwest corner is where you have all your strong reactions. And you can talk about if they go faster or slower. But this will be something that when you're processing the data, you will be determining, you'll be trying to get big Ks and little Ks, and that's what our month of May is going to be like. The main thing is you start off with a baseline, you inject your sample. You see your sample, your line goes up if your sample's binding. If you have more sample in there, your line will go up farther. You stop injecting your sample, and the line starts to go down because stuff is falling off. If it's still up too far, then you regenerate it, and what the regeneration means is you add a harsh chemical to break all these interactions and bring it back to baseline. We have pretty good regeneration conditions right now because we have worked with this particular fragment before, so it should work, and we should be able to do all steps of this. The only important thing from this, if I say we have to regenerate the chip, what that means is we have to knock off all the stuff that's still stuck on there, and we have to return to baseline to do another injection. So it's the curved part, and the curved part tells us not only how much binds, but how fast it's binding. The flat part is when we're coming to equilibrium, and that tells us how much is binding, not how fast it's binding. That's chapter 4. This is just another way of doing it. What I like about this one, it actually shows you where your injection is. So buffer, analyte, buffer, regeneration, buffer. This is what it might look like for you. But we'll walk you through this because I don't know what's going to happen until you see it. And this will just give you the words that we'll talk about when we get to it. Okay. The last thing that we do is we might do an automatic correction of the buffer using a reference cell. Remember how there were two cells? We attach protein only to flow cell 2. And then flow cell 1, we just leave it blank. That way, when the refractive index of the buffer changes, it's going to change both flow cell 1 and flow cell 2. But if we subtract out flow cell 1, then we will subtract out the reference change. We'll subtract out that sort of bulk contribution is what they call it. And then we will get a good real, this is just from our protein. It's not from our refractive index. Basically, flow cell 1 is our inline control. It's called the reference cell. And we use it to subtract out. The computer does this automatically for us. And just in your lab report, I'm going to give you some steps to take that apart and to show me this in the lab report from actual data. And that will walk you through that. And I've already talked about regeneration, so we don't need to do that. Regeneration solutions are kind of harsh. You can see that they have high salt, they have extreme pH, because you're trying to knock off that antibody that just won't let go, okay? But it's very specific to whatever your situation is, so you basically just try stuff and see what happens. And so that's the main thing. BIAcore is really amazing because you don't have to label. Anything that has mass, anything on this list, you can actually use up to whole cells. And we have a situation where we're going to actually use the whole cells that I will talk about. So to make sure that this is nice and recording, hopefully